Hello students, today we are going to see a very important topic, hybridization. For better understanding, kindly refer my previous video of valence bond theory, whose link is given in the description below. Let us start with the concept, hybridization. We know according to valence bond theory, the covalent bond is formed by the overlap of half-filled atomic orbitals. Also, the direction of overlap gives the direction of the bond. This is what we have seen in valence bond theory. If the covalent bond is formed by the overlap of half-filled atomic orbitals, therefore, the covalency of the element should be equal to the number of half-filled atomic orbitals possessed by it. However, on the basis of this concept, the formation of many compounds such as those of beryllium, boron, carbon could not be explained. Let us have a look at this problem. Here we have elements beryllium, boron, carbon, its atomic number and its their electronic configuration is written. See, the beryllium electronic configuration is 1s2, 2s2. It does not have any half-filled atomic orbital, which means it cannot involve in the overlapping of atomic orbitals. Therefore, its covalency is 0, which means it cannot form any bond with the other atoms. So boron, it has only one unpaired only one half-filled atomic orbital. This only will involve in the overlap of the orbitals. Therefore, it could form only one bond with the other element. The carbon has two half-filled atomic orbitals. Hence, it can form only two bonds with the other elements, according to this valence bond theory. So we may conclude that the beryllium has zero covalency, and the boron has only one covalency, and the carbon has only two valency, according to the orbital overlap concept in BB theory. But we know the beryllium forms compounds like BeCl2, in which case the covalency is 2, and the boron forms BF3BCl3, in which case the covalency is 3, and carbon forms enormous number of compounds with the covalency of 4. Okay. To overcome this problem, why this variation happens, to overcome this problem, it was suggested that one paired electron becomes unpaired in all the three cases. One paired electron becomes unpaired and jumps into the empty orbital, that is the next level orbital, empty orbital. Here see, one of the paired electron from 2s jumps into 2px, like this. This will become unpaired, this will become one electron here. Okay, now this will not come here. Also here, in order to get the covalency of 3, it has only one half-filled. Okay, in order to get covalency of 3, one of the electron from 2s jumps into 2p here, 2py. Here also, one of the electron jumps into 2pz. Now the carbon covalency become 4, boron covalency will become 3, and beryllium covalency become 2. Okay, and this is called excitation of electron. And where does the energy has come from for excitation? In order to excite one electron from 2s to 2px or 2s to 2py or 2x to 2pz, energy is required. Where does this energy has come from? The energy required for the excitation of electrons become available when the combining atoms approach each other. When the combining atoms approach each other, the energy is lost during that process. Say, for example, in the formation of beryllium chloride, okay, we have 2s atomic orbital of beryllium here, having 2 electrons, and the 2p atomic orbitals of 2 chlorine atoms are written here. When these 2p atomic orbitals approach the 2s atomic orbital of beryllium, in order to form the maximum stability, in order to form bond formation, in order to attain maximum stability, energy should be released in this process. Okay, the energy released during this approach is sufficient for the excitation of the electron. During this process, in the approach in the 2s atomic orbital approached by 2p atomic orbitals of chlorine, the energy is lost during this process in order to attain maximum stability. The energy lost is sufficient enough to excite the electron from 2s atomic orbital to 2px atomic orbital. So this happens, excitation happens. Now let us have a look at the formation of a methane, CH4. The central atom is carbon here. Its atomic number 6. Its electronic configuration 1s2, 2s2, 2px1, 2py1 in the ground state, that is isolated atomic state. In its ground state, it is 1s2, 2s2, 2px1, 2py1. According to the orbital overlap concept, it has only 2 half-filled atomic orbitals, so it could form only 2 covalency, but it's not true. Right. Now what happened? The excitation happens. The excitation of one electron from 2s into 2pz. Where does this energy has come from? When all the 4 hydrogen atoms approaches this carbon, the energy is lost. The energy lost is sufficient to excite the electron. So we got the excited state 1s2, 2s1, 2px1, 2py1, 2pz1. This is the excited state of the carbon. Right. Now we got 4 half-filled atomic orbitals. That is, it is 1 2s and 3 2p atomic orbital. Now all these 4 half-filled atomic orbital 1 2s and 3 2p atomic orbitals going to combine with 4 individual hydrogen atoms, that is the 4 individual 1s atomic orbital of hydrogen with unpaired electrons. So this is the 4 hydrogen atoms, 4 1s atomic orbital of hydrogen with unpaired electron, right, half-filled atomic orbital. Fine, but what do you think? The bond formed between the 2s atomic orbital of carbon and 1s atomic orbital of carbon, the bond formed, covalent bond formed between this and the bonds formed between the 2pz atomic orbital of hydrogen, carbon and 1s atomic orbital of hydrogen. Similarly, the bond formed between this and another 1s atomic orbital of carbon, the bond formed between this and another 1s atomic orbital of carbon. All the bonds are of same energy. Do you think like that? The bond formed between this 2s atomic orbital of carbon and 1s atomic orbital of carbon should differ in energy from the bonds obtained by the 2p atomic orbitals of carbon and 1s atomic orbitals of 3 hydrogen atoms. The bonds have different energies because of the different extent of overlap. The bond has different energies. Am I right? However, this is not true in the as per the experimental data, because the experimental data show that all the bonds have equal energies. All the bonds, all the 4 bonds, carbon-hydrogen bonds in methane are on equal energy. But according to this concept, the bond formed between this and 1s atomic orbital of carbon-hydrogen is different from the bonds formed between these 3 2p atomic orbitals and 1s atomic orbital of hydrogens are different. So this is in disagreement with the experimental data. Also, the direction of bonds or the geometry of the entire methane molecule is also different. Because see, the 3 2p atomic orbitals are from 90 degree to each other. They are 90 degree to each other. Okay. So when the bonds formed between these 3 2p atomic orbitals and 3 1s atomic orbital of hydrogen are of 90 degree to each other. The bonds also of 90 degree to each other. And the bond formed between the 2s atomic orbital of hydrogen and 2s atomic orbital of carbon and 1s atomic orbital of hydrogen will be of any direction. Right. So this is also in disagreement with the experimental data, because the structure of the methane is tetrahedral with the bond angle 109 degree 28 minutes. So a new concept was introduced to explain this abnormal behavior of carbon in methane. According to this concept, all 4 orbitals of carbon having 1 unpaired electron each possess slightly different energies. They mix up these orbitals with slightly different energies. They mix up with their energies and then redistribute it in 4 equal quantities, thus giving rise to 4 new orbitals, each of them having same amount of energy. This is called, this concept, a new concept is called hybridization. These 4 atomic orbitals with a different energy, slightly different energies, mix up with their energies and redistribute into 4 equal quantities. You have 4 individual orbitals, so it redistributes into 4 equal quantities. Therefore, it gives rise to 4 new orbitals, each of them having same amount of energy. Let us understand this using a simple analogy. I have discovered 4 persons, 1, 2, 3, 4. So the person 1 having 10 rupees, person 2 having 30 rupees, 3 having 30 rupees, 4 having 30 rupees. So in order to obtain equal share, what they will do, they mix up all the money, they combine all the money, add all the rupees with themselves. The 10 plus 40, 30, 40, 70, 100. The total amount is 100. How they distribute into equal share divided by 4 becomes 25. Now each of them having 25 rupees. So similarly, the orbitals having different energies, they mix up with their energies and redistribute into 4 equal quantities. As a result, 4 new orbitals are formed with their equal energies. This concept is called hybridization. Okay. So another analogy for this hybridization, I have 1 liter of white paint and 1 liter of red paint. When they mix up together, what happens? The total volume will become 2 liters. Okay, the 2 liters of pink paint. The resultant color is pink. Pink is the intermediate color between white and red. So it is considered as a hybrid of white and red paint. So similarly, here the colors getting mixed up to get the intermediate color or equal, to get the intermediate color between them. So here also, in the same case, like this, orbitals also mix up with their energies in order to get equal energies for all new orbitals. That is called hybridization. So it is defined as like this. Hybridization is defined as the mixing of atomic orbitals of same atom but having slightly different energies. So when they mix up with their energies, so the distribution of energy takes place between them, redistribution of energy takes place between them, resulting in the formation of new orbitals of equal energies and identical shapes. This concept is called hybridization. The new set of orbitals formed are called hybrid orbitals. This phenomenon is hybridization. Okay. In the next video, we will see the salient features of hybridization and how the hybridization, the hybrid orbital diagrams are drawn for the different molecules, and what are the different types of hybridization. We will see in the next video. Thank you.